Right, I'm going to mostly talk about antifreeze proteins on ice and specifically using information about the size of the antifreeze protein and the surface coverage to predict the thermal hysteresis values. I will not be talking about a couple of other efforts, computing the kinetic coefficient for curved ice-water interfaces and supercooled ice-water interfaces, and also antifreeze protein adsorption rates from an oriented attachment model. These are both sort of critical aspects of other theories, and particularly critical to the Sander and Shevchenko model. I will visit that point later in the present talk, but two of the key parameters that theory uses, treats as adjustable parameters actually, are things that we've now computed with simulations and with theoretical analysis. For now, I'm going to talk about this Farag and Peters model. This is work by Hossam Farag and myself. All right, so what do we know about antifreeze proteins? Well, they're found in many organisms. You don't have to go to such exotic organisms in order to find this capability. So a lot of insects have these things. A lot of fish have them, particularly in Arctic regions. Plants make antifreeze proteins. And one of the familiar organisms that will have it that might be found in your house if you have any reptiles as pets, you buy mealworms to feed them, and these make one of the super hyperactive antifreeze proteins, one of the most potent ones. So how potent are these things? This is a millimolar concentration axis, and this is measuring the potency of different antifreeze proteins in terms of the degree to which water can be supercooled. And still, these antifreeze proteins at this concentration can hold back the growth of ice down to that temperature, 0.01 even millimolar, which corresponds to a micromolar concentration of antifreeze protein. Solution is enough to still give you a couple of degrees of protection from freezing. Antifreeze proteins have a lot of different structures. In many cases, they have these rigid motifs. They often have these repeat units, length scales that are commensurate with the repeating patterns of the ice crystal lattice. Why are we interested in antifreeze proteins in the first place? Well, there's a lot of potential applications in the areas of cryopreservation, in food science, crop protection, and in de-icing of plates. Antifreeze proteins are thought to have a couple of key things that make them work. One, they must irreversibly bind to the ice surface and create dispersed pinning sites. There's a lot of evidence that these things bind to ice surfaces. You can directly see it by putting GFP tags on them, as done in this work by Konrad Meister in 2018. Theory of adsorption is something that we've worked on quite a bit, and I won't talk about that in the talk today. Second key ingredient is that as the ice tries to grow around an adsorbed antifreeze protein, and the ice bulges up around it, that curvature counteracts an outward driving force for the ice to grow into the surrounding aqueous phase. So you've got these pinning sites shown here in red and this bulging ice surface. As the supercooling gets deeper and deeper, the metastable equilibrium between the curvature and the ice surface results in stronger and stronger curvature. Now, eventually, given a distance between these two antifreeze protein pinning sites, that curvature will become so large that basically at the location of the pinning site, the ice surface will become vertical. And at that point, there's absolutely no more resistance to further growth of the ice surface out between these two pinning sites. Now, you can modulate how deeply supercooled this can get and still have a resistance to engulfment by either increasing the supercooling or by moving the two pinning sites farther apart. So increased supercooling and moving the pinning sites farther apart both make that situation more vulnerable to ice overgrowing those pinning sites. So these ideas go back to Raymond and DeVries in PNAS in 1977. They've been elaborated and expanded upon by many others in the years since. But basically, they already in 1977 proposed this Kelvin equation that says that the critical supercooling at which all metastability is lost, so this is almost like a spinodal condition for a complete loss of metastability, occurs when you have this relationship between the interfacial free energy, the melting temperature, the latent heat, and the distance between the pinning sites R. So the analysis done here is for like a one-dimensional array of pinning site locations in this one-dimensional, almost cylindrical kind of geometry for the curved surfaces between pinning sites. But in practice, this is not a one-dimensional array. These things are pinning sites on a two-dimensional lattice. So this has been called stones on a pillow. And a nice analysis of this situation, this sort of extension of the original metastability condition done in recent work by Amish Patel and coworkers. They derived that the critical supercooling, again, like a spinodal condition, occurs when you have this relationship between, again, the same variables, interfacial tension, a melting temperature, a latent heat. We still have a dependence on the distance between the pinning sites. That's now an L squared dependence. So that's a key change in the formula. And also you see in Amish's formula the occurrence now of a new variable that matters, and that's the size of the antifreeze protein. So sort of the radius B of these little black dots shown on the surface. There's a lot to like in these formulas. One is that as the distance between antifreeze proteins in both cases, as they get closer and closer together, predicted thermal hysteresis goes up. Also, as the antifreeze protein size increases, then the resistance to engulfment goes up there too. Of course, the Raymond and DeVries formula says nothing about that, but Amish and coworkers, their formula does get that qualitatively correct. There are also some downsides to this, right? So both formulas are derived for regularly spaced antifreeze proteins. And we know that these things are really, really quite random. Now, if they are random, the formula says that they will be engulfed at all these different temperatures, then there's a key observation that these theories, based on a spinodal limit to the metastability, they really can't explain. And that is that as you start from freezing and you supercool ice, the ice doesn't grow, it doesn't grow, it doesn't grow, and then all of a sudden you hit this critical moment where you get this like burst of growth and little spicules of ice grow out in all directions. Of course, these theories do predict a particular supercooling at which all of the antifreeze proteins will simultaneously get engulfed. But that is really an artifact of having a uniform spacing between all of the antifreeze proteins. In reality, these things are certainly going to be at variable distances from each other, and therefore they should be getting engulfed at different times. And that's something that really these two frameworks can't explain. We also know that nucleation tends to happen before you actually reach the spinodal condition. And likewise, we expect that engulfment is going to happen before we have a complete loss of metastability. And so these are theories based on that complete loss of metastability, and probably they are therefore going to be upper bounds on the true thermal hysteresis values. Can we go beyond these thermodynamic stability limits in these spinodal calculations in predicting the thermal hysteresis value? Well, we're not the first group that has tried that. Sander and Tchachenko published a beautiful paper in Physical Review Letters back in 2004. Their theory was based on a steady balance of adsorption, engulfment, and overgrowth rates. This identifies the critical supercooling at which a steady rate of growth at colder temperatures stalls. It also gives a number of points that agree with the experiment. It tells you that this critical supercooling gets larger as the antifreeze proteins get closer together. That agrees with the experiment. And it does a pretty good job of fitting thermal hysteresis data. Ido Braslovsky's group has shown that as you vary the concentration of antifreeze proteins in the solution around the ice, the thermal hysteresis values increase in a way that can be fitted by theoretical equation that comes out of the Sander and Tchachenko analysis. It should be noted here that all of these fits have treated two parameters in the Sander and Tchachenko theory as adjustable parameters. In principle, those are things that we can now predict. There should be some effort to go back and check whether the predicted values for these parameters match the fitted values to check whether these are fortuitous fits or whether they're physically meaningful. There's also the question, should the antifreeze protein concentration in the bulk matter if adsorption is irreversible? In principle, the longer you leave it bathed in any concentration of antifreeze proteins, the higher the surface concentration will become, and perhaps instead of really looking at the concentration in the bulk, they are inadvertently probing incubation time and an incubation concentration that lead to differences in the surface concentration, and that's really perhaps what is driving these trends. The third point is that the experiments don't actually warm until steady state growth stalls. That's this description, what the steady state analysis in the Sander and Chachenko theory is predicting. Instead, what happens is that we're starting at zero with ice not growing and already coated with antifreeze proteins, and we gradually get colder and colder, and there's no growth until there's a moment when we get a sudden burst of growth. So it sort of highlights this point that there's a subtle difference between preventing growth and stopping growth that was already occurring. Sander and Chachenko model predicts the point at which growth that was already occurring will falter, and that's different from what the experiments are usually probing. How can we build a model for that situation? Well, first we want to also address the point of random pinning sites. This is a solution of the Germain-Poisson equation for a surface with random pinning sites. Each of these things locally looks like it has a little circular footprint. Right in the center of each one of these little dimples is a pinning site, and it creates a little circular dimple in the local vicinity. And we want to think of that circular dimple as being a surface of rotation where we have a red ice water profile depicted here. If I rotate that around the antifreeze protein's footprint, shown here is in red in the center of this circle, then that's gonna trace out the shape of that dimple. And that's the geometry in which we're working in this particular problem. So I want to think of this R max as being approximately half of the distance from this antifreeze protein to its neighbors. And of course they aren't in a ring around this central location. So this is going to have to somehow be a characteristic distance that we will determine in a couple of slides. This is depicting the side view of these profiles. So we know that when we are below that spinodal limit, that there's going to be a metastable profile shape depicted here in orange. So this is the metastable equilibrium profile for a given not yet at the limit of metastability. As we increase the driving force, that will move up. But also we can think about driving the system to larger and larger amounts of ice underneath this surface of rotation around this antifreeze protein. The orange defines the zero amount of additional ice, and then as you distort the orange towards the brown profile, you create more ice underneath this surface of rotation. You also create more surface area. And so there should be two contributions to the free energy in this problem, one for the bulk driving force and one for the penalty associated with extra surface area. And so we want to find this metastable profile and the transition state profile by driving along a coordinate delta n ice. And here's how we construct the variational free energy model. We have our volume of the ice protrusion in polar coordinates, the area of that ice protrusion. We use those to construct a free energy of the ice protrusion in terms of the latent heat, the supercooling, and the interfacial free energy with those area and additional ice functionals. And then we construct a Lagrangian basically to minimize the Lagrangian subject to requirement of a certain amount of additional ice and find the optimal shape of the ice water profile. So there's a little surface thermodynamics model with a Lagrangian optimization at every stage that allows us to drive the deposition of more and more ice until we reach a transition state where the free energy starts to come down again. So very much like classical nucleation theory, but in this peculiar geometry. What do the results give us? The free energy barriers are plotted in versus the supercooling in kelvins. So this is a dimensionless supercooling multiplied by the melting temperature. You can see that we go from 0.5 up to about 30 degrees of supercooling. That would be remarkably potent for a real antifreeze protein. The real ones are somewhere down in this neighborhood of the purple to blue results, less than 10 degrees of supercooling resistance. It also depends on how far apart, how big that distance is to the neighboring antifreeze proteins. So that's been non-dimensionalized. It includes both the distance to neighboring antifreeze proteins and also the radius of the antifreeze proteins. And those things matter too. So you've got all three variables built into this variational optimization to give me the free energy barriers as a function of those parameters. And you can see the calculation predicts that the barrier decreases with deeper supercooling. It decreases also with a smaller AFP footprint. And it decreases with larger spatial isolation of the antifreeze protein. So we're capturing these features that the other theories had done, but now we're saying something about the free energy barriers before you reach that spinodal condition where the barrier has completely dropped to zero. We can comment in this theoretical framework on the size of the barrier at conditions up here and say something about the rate and not just equate the thermal hysteresis with being at the spinodal. So there are a few parameters in the theory that are not adjustable parameters. These are just properties of ice and water and the size of the antifreeze protein. The colored dots here show results of the variational optimization. The black curves show results once we've done the variational optimizations, a symbolic regression to give us a simple model, a simple interpretable model of those results, right? The variational optimization is interpretable in the sense that the starting equations we understood, but the variational optimization is complicated, hard to write down any simple formula for the delta F double dagger. But symbolic regression finds a representation for that. So there are parts of this that are derived from theory. There are parts of this that are the symbolic regression model choices, and they're adjustable parameters. I put these in quotes here. They are adjustable parameters in the sense that we are using a calculation with no adjustable parameters to start, and symbolic regression gave us a good model of those. So they're adjustable, but they're not fitted to experiment in any ways. I think in a sense they don't count as adjustable parameters. So this is the expression, this first part here, corresponding to the limit 50 kT. That is what you get when ice is completely crowded on the surface with antifreeze proteins. As they move farther and farther apart, this Rmax squared term inside the exponential brings those barriers down. One of the things to note here is that even though we're now able to say things about the free energy barriers at conditions before you reach the spinodal, we do get a consistent spinodal limit prediction with the one of Patel and coworkers. If you just set this free energy barrier to zero, you recover a condition for the spinodal, and you find that that coincides with a critical supercooling that scales as 1 over the squared distance between the antifreeze proteins. So that is consistent with their results, and we're getting it from a different route. So how do we explain the sudden burst of ice growth at one particular temperature when we have all of this ensemble of antifreeze proteins at variable distances from each other on the surface? As you cool the system, each of these things is steadily getting more and more susceptible to engulfment at any moment. And the one that's likely to be engulfed first is the one that has the largest area that it's responsible for preventing growth in. Like it has the largest Rmax squared is the one with the largest area here. Now these little areas here, these are Voronoi tessellations of the surface, and what we've done is we've equated the pi Rmax squared to the area of that Voronoi cell around each of these antifreeze proteins. So this one corresponds to the one with the largest area and therefore the largest Rmax. When that one gets engulfed, it now is buried in ice, and all of the antifreeze proteins that were its neighbors now inherit some of the load of holding back ice growth. So now these become the most susceptible points to engulfment. That subtle increase in their Rmax values dramatically increases their rate through this exponential of the free energy. And that suggests that our first engulfment event might trigger an avalanche of subsequent engulfment events. So we want to examine whether this idea of one engulfment event triggering an avalanche of subsequent engulfment events works. So you can basically set this up as a kinetic Monte Carlo calculation. At time zero, we have antifreeze proteins, all these little orange dots here, and they've been colored. The more blue they are, the more susceptible to engulfment they are. So it's likely that one of these very blue points will be engulfed first. You wait a very, very long time, and nobody has been engulfed up to the time of 0.97 seconds, so almost one second while the temperature is steadily being cooled and nothing has happened. Then all of a sudden, the first engulfment event happens. It's this one right here. So that one gets engulfed after 1 second, and you notice that only hundredths of a second later, after all that long waiting time, the entire region around it, half of the surface, has now been engulfed. And that's what we mean by this avalanche. Now, This avalanche picture was anticipated by Molinaro and coworkers in one of their papers, but this I think is the first time that it's really been shown that it is borne out by equations in a quantitative model. And it also suggests a definition for the thermal hysteresis. It suggests that when you look at a small ice surface, you've got an ensemble of antifreeze proteins, and you can basically identify the thermal hysteresis value not as the simultaneous spinodal limit for all of the antifreeze proteins, but as the temperature at which the first engulfment event happens, which will then trigger an avalanche for all of them. And so we're going to identify that as our definition of the thermal hysteresis. In order to quantify that, turn that into a working model, we're going to need to know the distribution of neighbor distances. Start with a randomly placed antifreeze proteins as shown here in the orange dots and the Voronoi tessellation around them. What we want to do is to create a model for the distribution of the areas around these antifreeze proteins. And specifically, we're going to create a model for the distribution, go straight to the Rmax values that correspond to the pi r squared equals area mapping that I showed you before. There are theoretical analyses that suggest that the right model for this is a gamma distribution. You can derive the nearest neighbor distance as a gamma. The nearest two neighbors satisfies a gamma. Nearest three neighbors satisfies a gamma. When you start putting restrictions on these things that they aren't in the same quadrant as each other, then you still keep the gamma distribution. All of this can be found in the supporting information of our paper. As you keep building up this hierarchy of distributions, this gamma distribution appears to be preserved. So we propose this as a model, and then we use likelihood maximization to pull out the unknown parameters in here. The average number of neighbors in our Voronoi tessellation is 5.7 from the model, and the average shape factor in here is this alpha equals 3.4. The important thing is that the model in orange gives you a pretty good picture of a histogram of areas that we generate numerically. And so these points out here are the ones that we care about the most. These are the AFPs that are the most isolated from their neighbors, and they are the most susceptible to engulfment. And they're the ones that are going to trigger the avalanche. Now what we want to do is to use our survival probability definition, which is basically saying that we have an inhomogeneous Poisson process, to estimate the thermal hysteresis. And before we can do that, we're going to need the prefactor to predict the engulfment rates from barriers. Derived this prefactor, it is not an adjustable parameter. For example, you can plug in numbers here. If the antifreeze protein has an effective radius of 1 nanometer, that will give you a prefactor of 0.3 times 10 to the 8 per second. How do you derive this expression? That's a complicated calculation, and I think, to my knowledge, the only place where you can see the recipe to do these kinds of calculations is in this book on rare events. Check out chapter 18, and you can read how those things are done. You could also see it in this paper. So now what we're going to do is to take our prefactor, take our distribution for the AFP distances on the surface, and we're going to construct this inhomogeneous Poisson model. Well, basically, it's a very simple master equation as the starting point. We have that the derivative of the probability that engulfment has not yet occurred is proportional to the probability that engulfment has not yet occurred. It is also proportional to the sum over all the rates of all the possible engulfment processes that can still occur, which is all of them. So we have a sum over all the antifreeze proteins. We have a prefactor for each one of them, and we have our symbolic regression model. It tells us what the activation barrier is for every one of those engulfment events. That is an evolving quantity in time, because as time progresses, the ice surface is getting colder and colder, and that was affecting the free energy barrier as time marches on. So this is the mapping between time and supercooling. What we're going to do is to, instead of having a sum over all the antifreeze proteins, we're going to say that there's a surface of area A and a number per area that we represent by sigma. And then we have to keep track of not only how many are on that surface, but what is the distribution of their distances to their neighbors. And then that allows us to plug in, to replace this discrete sum by a continuous integral and still account for the area of the ice surface, the coverage of AFPs on the surface. A little change of variables here from T to delta T gives us a dependence on how fast you do the supercooling, and of course the prefactor just comes out of the whole calculation. How does it work? Well, we get TH predictions versus experiment. I'm going to cautiously remind you that there are really no adjustable parameters in this model. No adjustable parameters in the sense that we're not fitting data in order to get these results. These are coming directly from the properties of ice and the size of the antifreeze protein and nothing more. So, it's capturing all of these trends correctly. It is getting reasonable ballpark agreement with the size of observed thermal hysteresis values. Unfortunately, most of the data in the literature has been plotted not against coverage of antifreeze proteins on the surface, but rather against concentration. And so one of the things that we want to do before we move on from this work is to go back and revisit some of those protocols and see what happens when we begin to consider incubation time and the concentration of the solution in which the ice is being incubated before supercooling starts, what those surface coverages are, and check to see whether this also works for other antifreeze proteins. So I want to go ahead and stop there and thank the people who've done most of this work. So Hossam Farag will be leaving us and going to Argonne National Laboratory very soon. Ravi Adula will be leaving us and going to Bit Mesra soon. And Kartik Kamat is already off to AbbVie. Obviously, we're going to have some openings in this particular area in the near future. Valeria Molinaro and her students, Pavi and Ingrid, have done a lot to help us with these efforts. We've learned a lot also by talking with experimentalists, Ido Brazlovsky and Konrad Meister, and also Francesco Pisani. And last but not least, I want to thank the Air Force for support of this work under the MURI ICE project.